Maths Aspirants is a collective of mathematics students, research scholars, and faculty members across India, initiated by myself in 2007. And we used to arrange several online problem solving sessions, online test series to help the students to prepare for different national level competitive examinations. All of you know the next NET examination, CSER NET examination, is scheduled on the month of June. So we Math Aspirants Groups planning to organize a series of problem solving sessions to help your final round preparations. As a part of that series, today we have the second session, and we today have Ms. Jiya Johnson with us to engage a session on topology and functional analysis. Ms. Jiya completed her MSc from Cochin University of Science and Technology and qualified CSER NET with JRF as well as GATE examination, and now is a senior research fellow at IIT Madras. I'm sure that today's session will be really helpful to all of you in your final round preparations. She will discuss some problems from the areas of topology as well as functional analysis. I welcome everyone to this program. And also, I would like to express my gratitude and thanks to Ms. Jiya for joining with us.
So today we will be discussing some problems from topology and functional analysis. Functional analysis, in NET exam, very less number of questions will be asked. In topology also, around some 10-12 marks questions will be asked in an year. 2 questions from C part and 1 question from B part mostly. So we have collected some problems from topology and functional analysis. So without much delay, I think we will start. I'll share my screen now. So if you have any doubts or queries, you can ask in between. And it should be an interactive session. It's not like I am telling a question, I am telling the answer. You have to interact in between. Then only it will be useful so that you will not feel bored. Okay. So I expect all your cooperation from your side, and let's start now. Okay. And thank you so much for inviting me for the CSIR NET series. So in part B, we will have 3 marks questions, and if it is wrong, negative marking is there, minus 0.75. And in part C, each question carries 4.75 marks, which will be multiple select. Part B is multiple choice. So then these are the syllabus for topology. It's a very less we have to concentrate about basis, dense sets, subspace and product topology, separation axioms. In that mostly Hausdorff property is required, connectedness, compactness. So these are the topics from topology, and from functional analysis side, we can expect questions from inner product space and orthonormal basis regarding that. Okay, so we have took some problems from these topics and we will discuss it one by one. So I hope you are familiar with the definition of topological space. So what is the definition of a topological space? Hello? Topological space? Tell me.
It is a collection of subsets. We
have a set X and we have a tau. Tau is a subset of
collection of
subset of X. Yeah, it is a collection of subsets of X satisfying 3 properties. What are those properties?
Phi and X belongs to tau.
Phi and X belongs to tau.
And any arbitrary union.
Tau is closed under arbitrary union.
And tau is closed under finite intersection.
Okay, tau is very good. Tau is closed under finite intersection. Now, can you tell me some examples for topological space? What are the immediate examples coming to
Tau
your
is
mind?
closed or open.
What?
Tau is closed or open. Property of topology.
What?
Tau is second property and third property. Tau is closed or open under the arbitrary union and intersection.
Huh?
This is a closed or open.
Closed under arbitrary union of open sets. This closeness, it is not the
Okay.
closeness of
Okay,
that
okay.
thing. Like if we have
Okay.
I varies, I belongs to I, then it's union of ui's that should be belongs to tau. This is what I meant by closed under arbitrary union. That is, arbitrary union of open sets should also be an element in our space.
Okay.
Similarly, finite intersection of open set should be open. Okay, so now what are the examples coming to your mind?
Ma'am,
set of
Euclidean space and matrix space.
What?
Our set of X.
Euclidean space and matrix space.
Yeah, metric space is coming, Euclidean space is coming, and someone says power set, that is a discrete metric, discrete topological space. And
In discrete topological space.
yeah, immediately you will have in discrete topological space. Then you will be knowing this cofinite topology, co-countable topology. Then what else? Usual topology on R. Then what are the other things? Semi-open.
Lower limit, upper limit topology.
Yeah, lower limit. Or this you can write it as lower limit topology. So you have lower limit topology. So you have enough examples with you. So when you see a question, first of all, try to if it is related to a topological space, you just think what happens for these examples immediately, so that you will get some idea which all options you can eliminate like that. Okay. Now we can start from problems. So we can start with starters. So this is a question. Which of the following is an inner product on the space of all real valued continuous function on closed 0, 1? So what is the definition of an inner product? Are you familiar with inner product? Hello?
No, ma'am.
Okay. So inner product space, if X is a vector space, you will be familiar, right? So let X be a vector space over K, and an inner product on X is a function from X cross X to K such that for all X, Y, Z in X, it should satisfy three properties. Inner product X with X should be greater than or equal to 0, and inner product X with X should be equal to 0 if and only if X equal to 0. And linearity in the first variable, that is inner product X plus Y with Z, is equal to inner product XZ plus inner product YZ. And inner product KX with Y should be equal to K times inner product X with Y. And conjugate symmetry in inner product Y with X should be equal to inner product X with Y. So this is the definition of an inner product. Okay, now we have to identify which are the which of these functions are inner product on the space of real valued continuous functions on closed 0, 1. So first option, will it be an inner product? So here, will the linearity property will be satisfied? That is inner product F with or inner product F plus G with H. Will it be equal to inner product F with H plus inner product G with H? Will it be satisfied? Or simply you can take inner product, you can check whether inner product KF with H, will it be equal to K times inner product F with H? This condition, will it be satisfied?
K negative ആണെങ്കിൽ satisfy ചെയ്യും.
Which one? Hello. What is inner product KF with H? It will be equal to integral 0 to 1 K F of T G of T. So this will be equal to mod K integral 0 to 1 F of T G of T. Okay, whatever. So this will be equal to mod K inner product F with G. So it is not K, it is mod K. So this condition will not be satisfied. So this is not an inner product. Now, can you say whether this will be an inner product or not?
Ma'am, I think last one is correct.
Yeah, we will go there. This one, why it is not an inner product? We can use the same argument, right? We can check the same condition so that it will be contradicted. So this will also not be an inner product. Now what happens to this option? That is inner product F with G. It is defined as F of 0 into G of 0 plus F of 1 into G of 1. Will it be an inner product? It will be linear. Linear property will be satisfied. And we don't have to worry about the conjugate symmetry here because we are in a real valued space. So we don't have to worry about the conjugate, and this will be inner product F with F will be positive always. So the only thing we have to check is inner product F with F equal to 0 if and only if F equal to 0. If F equal to 0, then F of 0 equal to 0, so F of 0 square. So this is equal to F of 0 square plus F of 1 square. So if F equal to 0, F of 0 square will be equal to 0, F of 1 square will also be equal to 0. So then inner product F with F will be equal to 0. So now the question is, inner product F with F equal to 0, does it mean that F equal to 0? So we have inner product F with F equal to integral 0 to 1 F of T into F of T dt, which is equal to integral 0 to 1 F of T square dt. And we know that this is equal to 0. And we have one more condition. That is, F is a continuous function. F is a continuous function, then F of T square is a positive continuous function. And if it is 0 on an interval, if its integral is 0, that means what we can conclude from here?
F of T square equal to 0.
Yeah, we
And
can
so F of
conclude
T
that
equal
F
to
of
0.
T square which implies F of T equal to 0 for all T belongs to closed interval 0, 1. So this F is an inner product. So all these options are wrong. This is the right answer. Okay. So shall we move to the next question? The next question is, suppose F is a continuous non-constant function from closed 0, 1 cross closed 0, 1 to open 0, 1 cross open 0, 1. Which of the following is not true? So the options are image of F is uncountable, image of F is a path connected set, image of F is a compact set, image of F has non-empty interior. So what is the definition of compactness? When we say that a subset of a topological space X, when we say that this A is compact, then yeah, right. Every open cover of A admits a finite subcover. Okay. Then we say that A is a compact. A is compact. So in R, will it be a compact space, open interval 0, 1?
No.
No, it is not a. So we can take the open covering like this. So it won't be it won't produce a finite subcover. What about closed 0, 1? It is a compact set. Okay. So that's it. That's about compactness. Now, what is the definition of connectedness? So we have a topological space X. When we say that it is connected,
There exists no two open sets, no two non-empty disjoint open sets such that X is the union of those open sets.
correct. So this X cannot be written as, it is not possible to write X as A union B, where A and B are open sets, disjoint open sets. Sorry. Disjoint non-empty open set. Or else we can say that if X is connected, if and only if X equal to A union B open set and A intersection B equal to empty, implies either A equal to empty or B equal to empty. Now, if A is open, then B will be closed, right? Because A complement is B, so B will be closed. If B is open, then A will be closed. So what? So if A, so what will be the Klopen subsets of X if X is connected? Klopen means both open and closed.
X and phi.
Yeah, empty set and X are the only Klopen subsets of X. There will not be a proper subset A such that V is contained in A is contained in X and A is Klopen, because if A is Klopen, we can write X equal to A union A complement. So this will be open and this will also be open. So it will not be connected. So the only Klopen subsets of a connected sets are the trivial ones. Now, what is a path connected space? What is the definition of a path connected space? Suppose we have a topological space X. If we have 2 points X and Y, when we say that there exists a path between X and Y,
There
that
is
is
a continuous function
yeah.
from
If-
I to X
yeah,
such that f of 0 equal to X and f of 1 equal to Y.
Correct. So if all the points are path connected, then we say that the whole topological space is path connected. Okay. So now we can address our question. And you will be familiar with these results. Product of compact space is compact. The Tikhonov theorem. Continuous image of a compact space is compact. Continuous image of a connected space is connected. Continuous image of a path connected space is path connected. All these results you are familiar with, right?
Yes, ma'am.
Product of compact sets finite or infinite?
Any product, arbitrary product.
Thank you.
That is Tikhonov theorem. So now our question is, we had a function f from closed 0, 1 cross closed 0, 1. So which all options we can say? So this closed 0, 1 is a compact set. So the product of compact set is compact. So this f is a function from a compact space. So continuous image of a compact set is compact. And we know that this is a path connected space. So continuous image of a path connected set is path connected. So we can say that image of f is path connected, image of f is a compact set. Now these two options we have to decide. That is, image of f is uncountable or image of f has non-empty interior. So can you give an example of a function from closed 0, 1 cross closed 0, 1 to open 0, 1 cross open 0, 1 such that it has an empty interior, or can you prove it? So is it possible to produce a function, continuous non-constant function from closed 0, 1 cross closed 0, 1 to open 0, 1 to open 0, 1 such that the image of f has a empty interior. Can you produce any counter example, or can you prove that image of F has non-empty interior? So this is our closed 0, 1 cross closed 0, 1. This is our open 0, 1 cross open 0, 1.
Maybe line.
F of xy equal to x0 something. x1
F
by
of-
2.
Yeah, f of xy equal to
X half.
x half. But then f of 0 y will be equal to 0 comma half. So the point will be lying here, which is not part of our image set. So whatever you said is correct. You can make it little more to this side. This x you can shift little bit. So like what to say? So you can map this to this line 0, 1. So that what map we can use from closed 0, 1 cross closed 0, 1 to. So 1 minute, I will add a page. Okay. Okay, see. So we have closed 0, 1 cross closed 0, 1. Now can you give me a map which maps to closed interval 0, 1? From here to here. Can you define a map? Which map we will take?
X comma y goes to x.
Yeah, right. We can take the projection map. So here x comma y will be going to x comma 0. Now this will not be contained in open 0, 1. So we have to make it something which is contained in open 0, 1. So can you tell me a map which makes to move this line to 1 by 4 to 3 by 4? So then it will be contained in open 0, 1. That is shifting a little bit.
X by 2.
X by 2 plus
Comma z.
1 by 4, right? So if we put 0, the value will be 1 by 4. If we put 1, 1 by 2 plus 1 by 4, which is equal to 3 by 4. So now we can project to, as he said, x by 2 plus 1 by 4, comma 1 by 2. So this will belongs to open 0, 1 cross open 0, 1. So from here, what we will do is, so this is our open 0, 1 cross open 0, 1. This line will not be there in our image. So we will just shift to this region. So that image will be a line. So it will have an empty interior. So this statement is not true. Now, what is the option remaining to check? So once you are able to eliminate all the 3 options, obviously the other option will be the correct one. So image of F is uncountable. So how we will prove that image of F is uncountable? So we have certain properties. Image of F is connected, that we know. Now what happens if it is countable? If it is countable, then it will have an enumeration. So we can write image of F as y1, y2, y3, etc. Now a countable set, and we know that this F is a non-constant function. So it has more than one point in the image set. So a countable set other than singletons, can it be connected in R2? So we have R2. Hello. Why it is not connected? So suppose here is my y1 and here is my y2. And y1 not equal to y2, we know. So there exists a distance between y1 and y2, say some r. So why it is not connected? Or will we be able to produce a disconnection for R2?
Hausdorff property. We can
Yeah, we can make use of Hausdorff property. So we can make a ball, open ball, centered at y1 with radius some r/2, and we can make another ball centered at y or 1 minute. Okay. So likewise, we can make uncountably many balls around y1, right? Corresponding to each point from here to here, we will get a open balls. So we have uncountably many open balls. So is it possible to choose an open ball around y1 such that on its boundary there is no points from this image set? Is it possible to choose such a delta? We have uncountably many balls around y1. And in the image set, we have only countably many points. So obviously there will be a ball without any of these points. Because if all these uncountable things, all these uncountable circles, if it contains 1 point each, then the image set will become uncountable. That is not possible. We have the image set is countable. So we can choose a ball centered at y1 without containing any of these points. Y1 on the boundary, it will not contain any of these points. Y2, Y3, etc. So with that ball, we can give a separation for R2. That is R2, we can write it as B Y1 delta. We can give the question is about image of F. So we can write image of F as, B Y1 delta intersection with image of F union B Y1 delta closure complement. So this will be an open set intersection with image of F. So this will be a disconnection for image of F. But we know that image of F will be connected since F is continuous and the map is from a connected set. So image of F will be connected. So if we assume that F is countable, we are getting a disconnection for image of F, which is not possible. So image of F cannot be countable. Okay. Should I repeat this? Is it okay for you?
Please repeat again, ma'am.
What?
Please explain again, ma'am.
Okay. So, sorry. Okay. We have, suppose we know that image of F is connected. That is fine, right? Image of F is connected. Now, we are assuming that we have to prove that image of F is uncountable. So what we will do? We will assume that if it is countable. If it is countable, then it has an enumeration for image of F. So image of F equal to y1, y2, etc. Now, so we have R2 in our hands. So we have two disjoint points at least, y1 and y2. So what I am going to do is, I am going to draw open balls around y1 corresponding to each of these radius. So I can draw a ball like this. I can draw another ball around y1 like this. I can draw another ball around y1 like this. Okay, how many balls I can draw like this? Will it be countable or uncountable? Yes, uncountably many balls I can draw. And so I have uncountably many balls here. And we have countably many points here. So we have uncountable on one side and we have countably many points on the other side. So suppose all these y1, y2 are, suppose this y3 is sitting here and y4 is sitting here. Only in countably many balls, we have elements from this set, but still we have uncountably many balls. So we can choose a ball such that on the boundary of that ball, there will not be elements from image of F. Now, is it possible? We have uncountably many balls and we have countably many points. So maximum on this countably many balls it can sit. But still we have lot of extra balls. So we can choose one from there. So we can choose a ball such that with centered at y1 and radius some delta, which intersect with image F, which is not intersecting with image of F. Is it fine now? Okay. Now we are using this. What? Hello. Now we are making use of this ball to give a separation for image of F. That is, we can write image of F equal to image of F intersection with ball. This I can write union image of F intersection with B y1 delta closure complement. Union image of F intersection with boundary. Okay, out of which this is empty. So we don't have to consider this side. So ultimately we can write it as, and this is an open set in R2. So this is open in R2. This is also open in R2. So image of F intersection A is an open set in image of F, and image of F intersection B is an open set in image of F. So this image of F, we are able to write it as the disjoint union of two open set. So which will contradict the connectedness of image of F. Is it clear? Okay.
Option 4.
What?
Clear, ma'am.
Okay, somebody asked about option 4. This one was option 4, right? That is, we are trying to show that there exists a continuous map from closed 0, 1 cross closed 0, from closed 0, 1 cross closed 0, 1 to open 0, 1 cross open 0, 1, such that image of F has an empty interior. Okay, so what is the immediate thing coming to your mind which has empty interior in this open 0, 1 cross open 0, 1? Like lines like this. So it will have an empty interior. So somehow we have to make a map from here to here such that this map is continuous. So for that, what I'm doing is, first I will map this closed 0, 1 cross to closed 0, 1, closed 0, 1 cross closed 0, 1 to closed 0, 1. So for that, we can take the projection map. Now, I cannot directly move to open 0, 1 because this endpoint 0 and endpoint 1 is not there in open 0, 1. So I am shrinking it little bit. So for that, we can use that linear map, x by 2 plus 1 by 4, whatever the map which takes closed 0, 1 to 1 by 4 to 3 by 4. Now again, if we simply put 0 here, again that will not be there in open 0, 1 cross open 0, 1. So somewhat shift towards the upward direction is also needed. That's why we just put half. Okay. Fine?
Yes, clear, ma'am.
Okay. Now we can move to the next question. Let X be a topological space and E be a subset of X. Which of the following statements are correct? E is connected implies E closure is connected. E is connected implies boundary of E is connected. E is path connected implies E closure is path connected. E is compact implies E closure is compact. So before starting this question, solving this question, I will introduce some other some other topics, not topics like proposition. Like this proposition you might have studied in your topology course. The closure of a connected subset is connected. More generally, if we have C a connected subset and C closure, whatever subsets we take in between C and C closure, that will also be connected. So this should be the, have you studied this result in your topology course? If C is connected, C closure is connected.
Yes.
Okay. So you are familiar with this one. Now, if E is connected, does it imply that A closure is boundary of E is connected?
No, ma'am.
Can you give a counter example?
Close 01.
Yeah, you can take closed 01. What will be its boundary? Its boundary will be set 01, which is not connected. So this example you can eliminate. Now, E is path connected. Does it implies E closure is path connected? And E is compact. Does it implies E closure is compact? So I will introduce some examples for you. So are you familiar with topologist sine curve?
Yes.
So topological sine curve will give many examples and counter examples for the topics like connectedness, path connectedness, locally path connectedness, such topics. So topologist sine curve is defined as like if we will be having this. Okay, 1 minute. So we will be able to plot the graph for x comma sine 1 by x when x greater than 0. So the graph will be something like this. It will go up and down like that. And along with this graph, together we will attach this part of y-axis. From here to here, we will attach this y-axis part. That is topologist sine curve. Okay. Will it be connected?
Yes.
Yes, it will be connected. Why? Because this will be connected. B will be connected. And X is in fact the closure of B. So if B is connected, then its closure will be connected. So our X will be connected. Now, will it be path connected? Path connected means if we take 2 points in that space, we should be able to produce a path between them. So will we be able to produce a path between any points of this space? Will it be path connected?
No.
Hello? Which points you are not able to connect? If we take 2 points from here, we will be able to connect. If we take 2 points from here, we will be able to connect. So individually they are path connected. So if we take 1 point from axis part and 1 point from the graph, then we will not be able to produce a path from this point to this point. Whatever path starting from this point, that will finally end up in a path which is contained in this axis only. So we will not be able to move from here to here. So it is not path connected. Okay. So similarly, you can ask questions like, is it locally connected, locally path connected? If you are interested, you can check whether it is locally connected, locally path connected. All these questions you can check. Okay. Now I will move to the next interesting example, broom space. Broom space is defined like we will take 0 and 1 by n's. Angles we will take it as 0 and 1 by n's, and we will draw each line like this. Okay, so this is also a topological space. Is it connected?
Yes, ma'am.
This is connected. Is it path connected? Will we be able to produce a path between any two points? Suppose if I take a point from here and I take a point from here, will I be able to produce a path?
Yes.
Yes, we can take this path. Right. My drawing is bad, but what I meant is going from this through this line, reaching at origin, and from here to here, moving like this. So is this path connected? And you will be knowing the result like path connected implies connectedness. So similarly, you can check the connectedness and path connectedness of Combs space. Combs space is putting lines at the points 0 and 1 by n. And you can check whether it is connected, path connected, like that. Now I will introduce one topology. I think some of you might have heard of it, VIP topology. So VIP topology is defined like...
Ma'am, the previous one was also path connected. No?
Combs space. This one, Combs space? Yes, it is connected as well as path connected. Because if we take 2 points, we can move from here to here through this line. From here to here, we can move through this line. From here to here, we can move through this line. So we can connect any 2 points. Now we will move to the example VIP topology. It is defined as let X be a non-empty subset and A belongs to X. So we will fix one element in that space. And the open sets are defined by subsets of X which contains A. So if we consider natural numbers and if my VIP element A is equal to 1, then set 1, 2, 3. This will be an open set. But set 2, 3 is not an open set because 1 does not belongs to this set. So here 1 belongs to this set. Here 1 does not belongs to this set. If 1 belongs to this set, this is an open set. If 1 is not belonging to this set, it is not open. Okay, so this is how we define the VIP topology. So what are some properties of this topology? Can you tell some properties of this topology? Will it be Hausdorff?
Every open set actually contains this element.
Yes, A.
So we cannot actually distinguish elements. We cannot separate points actually.
Yes.
So it cannot be Hausdorff.
Okay, so this is not a Hausdorff space. Now, what will be the closure of the singleton set A? What will be the closure of a singleton set A? What is the smallest closed set? Set X, right? A closure will be equal to the whole set X. Because closure is the smallest closed set containing A. For all the open sets, we are defining it as for all open set A belongs to U. So A does not belongs to U complement. So these are the closed sets of this topology. So A will not be there for any closed set. A will not be there for closed set only except for full set X. Is it okay for you that closure of A is the full set? Should I repeat? What are the open sets of this topology? Open sets of this topology are subsets of X which contains A. So, which are not open or which are the closed subsets of A of this topological space? Closed subsets are complements of open subset, right? So for complements of open subset, what is the property? A does not belongs to U complement. So closed subsets of this topological spaces are, we have to take complements for each open set. So complement of empty set is full set. Now complement of each set which contains U, that is subset V subset of X such that A does not belongs to V. So these are the closed subsets. Okay. So except for A, the whole set, for all other whole closed subset, A is not there. So set A closure is the smallest closed set which contains A. So it will be equal to the whole set. Is it okay for you?
Yes, ma'am.
So
How do you say it was a smallest one?
because these are the other closed subsets of this topological space. In all these closed subset, A is not there. So suppose this is our A. All these closed sets are away from A. So these are V. V's are coming like this. So set A closure is the smallest closed set containing set A. All other closed sets are keeping a distance, not a distance. So all other closed sets are away from A. It is coming like this, like this, like this. The only closed subset which contains A is the whole set. Should I repeat once again?
Okay, ma'am. Understood.
Okay. So this is a weird example in the sense like set A is a singleton set, but its closure is becoming the whole set. Okay. So all these examples you can keep in mind to answer our questions. So what were the options? Do you remember? Okay. So this was our question. So E is connected implies E closure is connected. Is it true or false?
True. True.
True. Now E is connected implies boundary of E is connected. That we discarded.
False.
Now E is path connected implies E closure is path connected. Is it true?
False.
False.
False. Which counter example you can produce?
Topology sign curve.
Correct. Now E is compact implies E closure is compact.
No. True. False.
Why?
By taking VIP topology on R.
So singleton sets are always compact, but its closure is not compact. Right. So this is the answer. So now you
Can
can
you
try.
explain the option third again?
What was option 3?
Yes.
Option 3 was topologist sine curve, right?
Yes, ma'am.
So topologist sine curve is, what was option 3? E is path connected implies E closure is path connected. So as E, you can take this B. So here B is path connected, but B closure is not path connected. B closure will be the whole topologist sine curve. So this is not path connected, but this is path connected. Okay. So now this is a similar question. A connected, A closure connected, A path connected, A closure path connected. All these blah blah things that you can do yourself. Okay. This in this question, which of the following statements are true about the subsets of R2 with the usual topology? A is connected if and only if A closure is connected. That you can check yourself. Intersection of two connected subsets is connected. Is it true?
Need not be true.
What example you can produce?
Two disjoint intervals.
Two,
Disjoint intervals.
if if we take two disjoint intervals, its intersection is empty.
Some two open balls meeting at S point actually. In R2. Two open
Two
balls
open
intersecting at exactly 2 points.
Okay. Coming like this.
Yeah.
So its intersection will be this. It's again connected. So if we want to produce a counter example, like intersection of two connected sets connected. So the intersection has to be disconnected. So in that way, you have to think. So these two balls, is it disconnected? It is disconnected. Now, can you make it as intersection of? Huh?
Just boundary, not full ball. That boundary is on.
Okay. This one now.
And boundaries of that open balls. That two open balls boundaries are actually connected, right?
Yes. So you are talking only about the boundary.
Yeah. Not including the interior. Excluding the interior actually.
So
just that 2 points.
So then you are telling these 2 points. You are taking open balls or closed balls?
Boundaries of that open balls actually.
Okay, you are taking the...
Just the boundary, not the closed or open ball actually. Just the...
Okay, only the boundary you are taking.
Yeah.
So its intersection will be these 2 points. Okay, fine.
Yeah.
Okay, good. Okay, so intersection, or you can think something like this. So that intersection will be this region, which will be disconnected. So likewise, you can produce many examples. Intersection of two connected sets need not be connected. So this you can eliminate. Union of two compact sets, is it compact?
Yes, compact.
That will be compact. Now only this option we have to check. There are exactly two continuous functions from Q2 to the set 0, 0, 1, 1. So what can you say about this option? We can, two continuous functions, you can immediately say the whole Q2 mapping to this point, that is one continuous function. The whole Q2 mapping to this point, this is another continuous function, because all these are constant functions. So other than these two continuous functions, will there be continuous functions from Q2 to this set? Q2 means Q cross Q. Will there be other continuous functions to this 2-point set?
Yes.
It is not possible because if we take any other function such that at some point the image is 0, 0 and for some point the image is 0, 1, 1, then since it is continuous, so it must attain the in-between points which is not in the real set.
You are telling this intermediate value theorem. So for that, the function should be from R to R kind of thing. But here it is topological space. So here the topology will be on the left side, we have Q cross Q. So the points will be lying somewhat like this. So this is the subspace topology from R2. On the right hand side, we have 2 points, 0, 0 and 1, 1. So here we have subspace topology from R2. So here, this is our Q cross Q. To this 2-point set 0, 1, 0, 0 to 1, 1. So what will be the subspace topology on this set, on this 2-point set from R2?
Discrete.
Discrete. So on the right hand side, we have discrete topology. On the left hand side, we have Q cross Q with subspace topology from R2. So this intermediate value theorem and all, it need not hold in topological space. All those things we proved for this real analysis from R to R kind of things. So you cannot apply intermediate value theorem. Or can you produce some other continuous function from Q cross Q to R? Sorry, not to R, this 2-point set. Is it possible?
The inverse shall be disconnected.
Q cross Q is disconnected. So you can use that disconnection.
Yes, by taking some irrational root 2.
Yeah.
And
So this
with
is how your
making a
root 2,
bowl.
this is minus root 2. You can make it as a square kind of thing. So here also
Then
root 2, this is minus root 2. So this Q cross Q, you can write it as this rectangle, this square, this including this interior, I am calling it as S. Boundary, I am calling it as boundary of S. This is S closure complement. So this Q cross Q, you can write it as this S is open. S intersection Q cross Q union S closure complement intersection Q cross Q. So this will be a disconnection for Q cross Q. So now you can send this part to 0, 0 and this part to 1, 1. So that this will become a continuous function. Why it is a continuous function? So inverse image of open set has to be open. So inverse image of this singleton is S closure complement intersection with Q cross Q, which is open. And in inverse image of this point is S intersection Q cross Q, which is also open in Q cross Q. And the inverse image of whole set will be the whole Q cross Q, that is fine. Inverse image of empty set will be empty set. So this will be a continuous function. Likewise, you can produce many more continuous functions. Right. So
Positive side goes to 0, 0 and the negative side goes to 1, 1.
you're considering what happens if it coming like this up. So that one will go to 0, 0 and the other will go to 1, 1.
No,
Is it
no,
the
I
problem?
give another example. Is it continuous?
Okay. From word to word?
Positive axis, positive x comma y both are positive goes to 0, 0 and negative x comma y or negative goes to 1, 1.
X comma, if x and what happens if x is positive and y is negative and x is negative, y is positive, all those parts. And what happens? So for your function, you are making x comma y, and if x and y both are positive, you are defining like this, right?
Nice.
And if x is less than 0 and y is less than 0, you are defining it as x comma y equal to 1, going to 1, 1.
Yes. Above
Okay.
x-axis and below x-axis, like that.
Like you are taking y positive and y negative. Is it like that you are taking? So in that case, what happens if I take a sequence converging to 0, if I take a sequence converging to 0 from this end and from this end, so that will contradict the continuity, right? Because you can take sequence which is converging from above and converging from below. So above it will be going to 0, 0 and the below will be going to 1, 1, whatever is your map. So it need not be, it is not continuous map, whatever you said. So now this question you can try yourself. It's again connected. You go use connected. You can try with examples from close to 0, 1 to whatever. Now this is another question. Consider the function f from C to C given by f of z equal to e power z. Which of the following is false? So f of z belongs to C such that mod z less than 1, it is not an open set. Z belongs to C such that mod z less than or equal to 1. Z belongs to C such that mod z equal to 1. Z belongs to C such that mod z bigger than 1. So its options are like whether it is open, closed, like this. So are you familiar with open mapping theorem in complex analysis? So there is one theorem, open mapping theorem in complex analysis. A non-constant analytic function will map open sets to open sets. So e power z is a non-constant analytic map. So it will map open sets to open sets. So this is an open set in C. So its image will also be open. So this is wrong. Now this is an open set in C. So its image will be an open set. And it will be unbounded also. So this will be true. Now what happens if whether it to this option? So this z belongs to C mod set less than or equal to 1. This is a compact set. So image of f will be a compact set. So a compact set in C that will be closed. So if it is open, then that will become a Klopen subset of C. So what happens is, we know that this is closed anyway, because it is the continuous image of a compact set. So this will be closed. That is, we are sure. Now, the question is, it is not an open set. If possible, if it is open, then this set become an open subset as well as a closed subset of C. But C is connected. So it is not possible. So it is not an open subset. So it is not an open set. The statement is true. Now, what about this option, third option? Is it okay? Option B, is it fine for you? Should I repeat option B?
Yes, please repeat.
The question is, here this is a compact set. Continuous image of a compact set is compact. So I am calling this set B equal to f of this thing. So B is a compact set, that we know. If B is compact, that means B is closed. Since we are in C. Now, so this B is closed, we know. The question is, the statement is, it is not an open set. So if it is an open set, if B is open, then B is closed also. So B is open, B is closed. That is, we are getting an open and closed Klopen subset of C. But C is connected. So it will not have non-trivial Klopen subset. So that will make a contradiction. Why that contradiction happened? We assumed that this set is an open set. So it is not an open set. So this B is not an open set. So this is a true statement.
In that case, what is the role of the function f over here? Because we are just looking at the range.
Yes. Here we are not using any properties of e power z. We are just using that open mapping theorem. For applying open mapping theorem, we should know that the function is non-constant and function is analytic. So only that much property we are using. Instead of e power z, whatever be the function like sin z or whatever, we can use the same theorem. It doesn't play much role in this question.
Okay.
the function definition. So now next is f of z belongs to C such that mod z equal to 1. Again, this is a compact set. So its image will be compact. So it will be closed. So this option is also true. So we have to mark which of the following is false. So we have to mark option 1. Is it clear?
Yes, ma'am.
Yes, ma'am.
Okay. Now consider the space S is equal to alpha B where alpha B belongs to Q. That is Q cross Q. So here we have Q cross Q. Now whether Q cross Q is it connected in R2? We have done before. We were able to produce a disconnection. Like root 2 cross that taking that rectangle. So inside and outside. So that we were this rectangle I called it as S. And this boundary, this is S closure complement. So we were able to produce a disconnection for Q cross Q. So it is not connected. Now what about the complement of Q cross Q in R2? Will it be connected?
Yes,
Or
ma'am.
yes, why? R2 minus any countable set will be connected. Why?
That will be path connected actually.
Path connected, very good. So if we take 2 points, say some y1 and y2, we will have uncountably many paths from y1 and y2, out of which only countably many points are removed. Still, there will be a path from y1 to y2, which is completely contained in this Q cross R2 minus Q cross Q. So this will be path connected. Okay. Now we will move to part C, the main course. So we can start with an easy question. Let x is equal to n union infinity comma minus infinity. So here infinity and minus infinity are just symbols. Let tau be the topology on x consisting of subsets u of x such that either u contained in n or x minus u is finite. So the topology, there are two possibilities. Either open set, it should be completely contained in n, or the other set of open sets are sets whose complement is finite. So let A is equal to n union infinity and B is equal to n union minus infinity. Which of the following subsets are compact? A, will it be compact? Or what are the open sets containing infinity? Open sets has two possibilities. Either it should be subset of n, or its complement has to be finite. So if we have one element infinity, this set of open set, there will not be open set of this form. So we have to look open sets of this form to include infinity. So the open set will be, if this belongs to an open set U, then what does it mean? X minus U is a finite set. We can call it as some n1, n2, etc., nk. So A is equal to n union set infinity. So if we take an open cover for A, such that ui, I belongs to I, there will be one u1, say, which where infinity belongs to that u1. Now only finitely many points are remaining. So now you can choose u2 which contains n1, u3 which contains n2, etc. uk plus 1 which contains nk. So by these many open set, we can cover the whole A. So this A will be a compact subset. Is it okay?
Yes, ma'am.
Okay. So this A will be a compact set. Now, what is X minus A? What is the set?
Set minus infinity.
Set minus infinity. Will it be compact?
That is a finite set.
Yes, it is a finite set. So obviously it will be compact. Now what about A union B? What is A union B? A union B is X itself. Will it be compact?
Yes.
We can use the same argument, right? For
Yes.
we used A. Okay. So this is compact. Now what about A intersection B? A intersection B is N.
Yes.
Will it be compact?
Ma'am,
No.
I'm saying that whenever
It
we
won't be
include
compact.
infinity,
You can take
What?
singleton.
Yeah, you can take singleton 1, singleton 2. This cover you can take, which will not produce a finite subcover. So this is not compact.
somehow A union B is compact.
What is A union B? Union B is the whole set. So there will be points infinity, and so if you take you can use the same argument. You will start with an open set which contains infinity. So it will exclude at most finitely many points. Now you can take the open sets which contains that points. So the same argument will work for A union B as well. Is it okay? Hello?
Okay.
Okay. Or else you can think like this. This A is compact. Similarly, this B will also be compact. So A union B will be compact. So in like that also you can think.
Ma'am,
Ah.
if we choose singletons or finite cover, singletons are open sets. Then what about the option 3?
If singletons are open, you can take singletons. Then A union B equal to N union set infinity and minus infinity. So there should be an open set containing infinity and there should be an open set containing minus infinity. So that open set, we can eliminate many of this. So suppose this U is an open set containing infinity. Then U is equal to the whole set minus finitely many points. Say some 1, 2, 3, 4. Okay. So in that case, you can pick 1, 2, 3, 4. All this you can pick it up and together with this U. And maybe one more set with which containing minus infinity, that I am calling it as V. So with this 6 elements, you can cover the whole N. Whole X.
Thank you.
Okay. Now, next question is, any compact topological space is matrixable. When we say that a topology is matrixable, if the open sets are generated by a metric, right? So ultimately, if a topological space is matrixable, then it will be a metric space. So now the question is, any compact topological space is matrixable. Is it true?
No, because
What?
cofinite topological space is not matrix.
Yeah, cofinite topology. You mean on countable set? Cofinite.
Uncountable set.
Countable or uncountable is finite. Fine.
Becomes
Yeah. Right. So that will be a compact topological space which is not matrixable. That is correct. Or else you can simply start with if we have X is equal to set 0, 1. You can define do you know Sierpinski space?
Yeah, just singleton A, B.
Correct. So that is also a topological space which is compact, but it is not matriceable. Now, next question is, any continuous image of a Hausdorff topological space is Hausdorff. Is it true?
False. False.
Which counter example you can give?
From discrete space to indiscrete space.
Yeah, correct. So we can take, say, the same example from X to X. Here you are putting discrete. Here you are putting indiscrete. So you are taking the identity map, right? Okay. So continuous image of a Hausdorff topological space need not be Hausdorff. Now what about fourth option? Intersection of two connected subset of R with usual topology is either empty or connected. So what are the connected subsets of R?
Intervals.
Interval.
Intervals. What will be the intersection of intervals?
Again an interval or empty set.
Again an interval or an empty set. So all the intervals are connected. So intersection, so this is a true statement. Intersection of two connected subsets of R is either empty or connected. Now what about the third option? That is, if f from X to Y is continuous and 1, 1 and Y is Hausdorff, then X is Hausdorff. Is the statement true? So we have two spaces, X and another space Y. And here we have a map F. Whatever be the questions from topology, try to figure it. Try to draw the figure correspondingly so that you will get an idea. Now, what are the things given? F is a continuous function. And we know that F is 1, 1. And this Y is Hausdorff. Now, the question is, will X be Hausdorff? So, in order to check whether X is Hausdorff, we have to start with two distinct points. Now, somehow we have to make use of the Hausdorffness of Y. So, here we have X and here we have Y. So, there will be corresponding f of X and f of Y. Will it be distinct?
Yes, because on one.
Because it is 1, 1. So, we have two distinct points in another Hausdorff space. Y.
Then
so, now
separate them
can
with
you
Hausdorff.
separate? Yeah. So, here you can separate it. F of X and f of Y. Call it as U and V.
Pull back to X.
Now pull back to X. So here you will get F inverse of U and here you will get F inverse of V. So that this F inverse of U and F inverse of U will be open. Why it is open?
Continuous.
Continuous.
F is continuous. Then F inverse of U intersection with F inverse of V will be empty. Okay. So this is a true statement. Now we can move to the next question. Let XT be a metric space and let f from X to X be a function such that distance between f of X and f of Y is less than or equal to. This you can try yourself actually. I will move to the next question because if we have time, we will come back to this question. Now we will move to this question, a question from functional analysis. Let T from X to Y be a bounded linear operator from a Banach space X to another Banach space Y. Which of the following conditions imply that T has a bounded inverse? So certain conditions are given. Okay. Now, which all theorems you are familiar with related to this inverse, Banach space to Banach space, continuous
Bounded
linear map? Correct. So somehow we have to make use of bounded inverse theorem. So what is bounded inverse theorem saying? Let X and Y be Banach spaces and T is a bounded linear operator which is bijective. Then T inverse will also be a bounded linear map from Y to X. Now we also know that let X and Y be Banach spaces, then T belongs to BLXY is bijective if and only if T is bounded below and range of T is dense in Y. This you might have seen in your functional analysis course. Is it?
Yeah.
Okay. So now suppose if I know that this T is bounded below and range of T is dense, then we can say that T is bijective. If T is bijective, then we can make use of bounded inverse theorem. Okay, so from which all options? So these two options guarantees that T of X is dense in Y, that is a range. So here range of, in these two options, we have the condition that range is dense in Y. But we need one more condition, that is T is bounded below. So the thing is, we have to ensure that which of these options will guarantee that this T is bounded below. When we say that an operator is bounded below, what is the definition? When we say that an operator is bounded below, when an operator is said to be a bounded operator,
Well, its image set is bounded.
when here it is a bounded linear operator. Bounded linear operator means it will take bounded sets to bounded set. That doesn't mean that image is bounded. If it is some zero function or something like that, it will be bounded.
If
But
there is
other than
some
that,
constant alpha such that norm T of X less than or equal to alpha times norm X.
yes, there exists an alpha positive such that norm Tx is less than or equal to alpha times norm X.
There exists a
So this
beta
is the
such that
definition.
beta times norm X less than or equal to norm Tx. We say it is bounded below.
So bounded below means there exists an alpha positive such that alpha times norm X is less than or equal to norm Tx. Right. So this is the definition for bounded below. Now, what we can say? If X is not equal to 0, we can say that alpha is less than or equal to T of X by norm X, right? Because T is a linear operator. So that means, so here, if you take it as Y, what you will get? Alpha is less than or equal to Ty. Sorry, here I have to put no. Alpha is less than or equal to Ty whenever norm Y equal to 1. And alpha is strictly positive. So which option will be correct then?
4.
Option 4 will be correct. That is, if infimum will be less than, so infimum of Ty such that norm Y, so alpha is less than or equal to infimum among norm Y equal to 1 such that norm Ty. But this is strictly bigger than 0. So this infimum of this thing, which will be strictly bigger than 0. So option 4 is correct. Now can you give counter examples for other 3 options? Can you give counter examples for other 3 options? Can you give an operator such that infimum equal to 0 but not invertible?
0 operator will work.
Yeah, you can take the 0 operator. What about for option 2? Option 2, it is bounded, it is not bounded below, right? It is bounded below, this alpha should be strictly positive. So if it is not bounded below, obviously it will not 1, 1. So can you produce a function which is not 1, 1 from x2 but somehow surjective? From any Banach space to, say, let x is equal to some L infinity to y is equal to that k. So this will look like x of 1, x of 2, etc. This is mapping to say some x of 1. So, sorry.
Shifting operator, something.
Shifting operator,
0, x of 1, x of 2.
so that you have to check what is the infimum. So here we can immediately say that this is not 1, 1. So then it will be not bounded below also. So this condition will be violated. But T of x is dense in Y. So this map will not be invertible. Now what about option 3? Option 3, what is the difference between option 3 and 4? In option 4, we have T of x is dense in Y. So that should be violated here. So that this image is sitting in a bigger space. So can you give some example for that? Which example you can say take? That is, it should be bounded below but not surjective. X to Y. T has to be bounded below but not surjective. Suppose we have T from C0 to C0, which is sitting inside L infinity. And if we take the identity inclusion map, so this we can treat as a map from C0 to L infinity. So x will be going to x itself. So norm Tx will be equal to norm x. So alpha is, so this is strictly infimum of Tx, that will be strictly positive. Will it be invertible? Will it be surjective? From C0 to L infinity, we have the inclusion map. So will it be surjective? L infinity is a bigger space than C0.
Yeah, we can take any sequence not converging to 0. It won't
Yeah,
have it.
so this map is not invertible. Okay, so all other 3 options we can eliminate. Okay, now we will move to the next question. 1 second. Before that, I will just, you can read this question. So which all options you can eliminate? Hello?
Yes.
These false
So
means
it's not good.
What?
D is a false option. It is a
A is not good. It's not good.
A is closed, that is wrong. B, is it closed?
Yeah.
yes,
Yes. True. Limit
Okay.
point
Now
will
what
be
about option 3 and option 4? A is homeomorphic to Z.
n going to 1 by n.
Okay. Homeomorphism, it has to be both 1, 1 and on 2. So your idea is correct. Like,
But 0. Okay.
kind of. That is fine only. Your
option D is
So-
false.
option
Option D is false.
D is false. Why it is false?
Because B being closed and bounded, it is compact. So the homeomorphic image of the compact space must be compact, but Z is not a compact space.
B is a closed and bounded subset. So B is compact, and Z is not compact. Okay, fine. Now what about option 3? Will A be homeomorphic to Z? What is the so A will what is the topology on A?
Discrete
Subspace topology. Yeah. So A we have discrete topology. On Z, what is the subspace topology on Z from R?
It is also discrete.
That is also discrete topology. So we have discrete topology from Z to on A as well as on Z we have discrete topology. And we have same cardinality for both the sets. So we can, since it is discrete topology on both sides, whatever be the function, it will be continuous. So if we have any 1, 1 on 2 function, that will be continuous from both sides because it is discrete topology. So as you said, if we take, say, on Z, 1 going to 0, 1 by 2 going to -1, 1 by 3 going to 1, 1 by 4 going to -2, 1 by 5 going to 2. You take this map 1, 1 and on to map. So this map, it is from A to Z. Since we have discrete topology on A, every map from here to here will be continuous. And if we take the inverse map from Z to A, since we have discrete topology here, that inverse map will also be continuous. So this A will be homeomorphic to Z. So this option is true. So now we can move to the next question. Let X be a topological space. The previous question was fine, right? Hello?
Yes.
Okay, so now it is let X be a topological space. Let A1, A2 be two dense subsets of X. When we say that a subset is dense,
It's closure equal to 4.
Closure is equal to X.
so A1 closure equal to A2 closure equal to X. Okay, now if E subset of X, then which of the following are true? E intersection A1 is dense in E. Will it be true?
Not necessarily true.
We can take Q complement R.
You can take A1 equal to Q and E equal to, you can take it as Q complement. So E intersection E1 need not dense in E. So we can eliminate that option. Now about the other one. E intersection A1 is dense in E. If okay, in the similar way, can you avoid some other option easily?
Yeah, C also, I think.
C also we can eliminate because A1 you can take it as Q, A2 you can take it as Q complement. So we can eliminate option 3 also. Now what remains is option 2 and option 4. Now suppose option 2 is true. Suppose. Can you conclude anything about option 4?
Yeah, again that will be E intersection A1.
We
I
can
think
apply this.
option B we can use Bayes category theorem something.
Bayer, do we have to use Bayer category theorem here?
No need.
Like suppose we prove option 2.
No, we don't have a completeness actually.
We can prove option 4 also because it is coming like if E intersection A1 is dense. Hello?
Yes, Miss. E intersection A1 is also open option 4.
Yes, this is open. So this is an open set. So what we can say, E intersection A1 intersection A2 is dense in
E intersection A.
E intersection A1. And E intersection A1 is dense in
E.
which is
Okay.
dense in E. So altogether E intersection A1 intersection with A2 will be dense in E. So suppose if we prove option 2 is true, automatically option 4 will also be true, right? Is it okay?
Okay.
So now we have to prove option B is true. That is E intersection A1 is dense in E if E is open. So how can we prove that? 1 minute.
Suppose dense definition is suppose any set is dense in R or X can find an open ball intersection with that space is not empty, then we can say the function the set is dense set.
I'm sorry, I couldn't hear you properly. So we have to check whether prove that E intersection A1 is dense in E. That is, if we start with that, so we have an open set E, and if we start with an element X in E, we should be able to produce an element in from E intersection A1 in whatever be the neighborhood of X. So let X belongs to E, and I am taking an open neighborhood of X, U. Okay, so then this E intersection U, will it be open? Hello?
Yes, ma'am.
So this will be an open subset. Now A1 is dense. A1 is dense. That means whatever be the open set, we will have a representative from A1. So we can get an element A1 from here in the set. So what is the peculiarity of this A1? This A1 belongs to capital A1 and this A1 belongs to E. That is, we are getting an element from E intersection A1. So whatever be the neighborhood we started, we are getting an element from E intersection A1. So E intersection A1 is dense in E. Is it clear? Should I repeat? Hello?
Once again repeat.
Okay. We have given that, forget everything. We have given that E is an open set. Now what we have to prove? E intersection A1 is dense in E. So if we dense in E means if we take any element X belongs to E, there should be if we start with any element X in E, there should be a sequence of elements. It's not converging kind of. Whatever be the neighborhood of X we are taking, there should be representative from this set. That is the definition of denseness, right? So we are taking an open neighborhood U of X. So this U intersection B will be open again since E is open and U is also open. So this U intersection E is open. And we know that A1 is dense. Since A1 is dense, there will be an element from A1 in this open interval. So that element I am calling it as little a1. Okay, so this little a1 belongs to E and belongs to a1. So we are getting a neighborhood a1, an element a1 which belongs to E intersection a1 and a1 belongs to U. So whatever be the neighborhood we started with for x, we are getting an element a1. Sorry, this is not a, it is a1. This is a1. So whatever be the neighborhood we started with for u or for x, we are getting an element a1 from this set. So this E intersection a1 is dense in E. So since option 2 is 4, option 4 will also be automatically true.
Can you please repeat option?
Option 2. When we say that a set is dense in, suppose A closure equal to X. Suppose A closure equal to X. What is the alternative definition of denseness?
It intersects every non-empty open set actually. A intersection V not equal to 5 for every
A intersection U
V
is non-empty. Okay. Non-empty for all non-empty
open sets.
Non-empty open set.
U subset of X.
Yeah, or no, for every open non-empty open set, U subset of X. This you know. Now, I will change the color. Okay. Now we have to show that whether E intersection A1 is dense in E. This is what we have to check. So, that is we have to check E intersection A1 closure equal to E. So for that, what we have to check? We have to start with an open set in E. So start with an open set in E. Call it as some call it as some B. So how this will look like? How this B will look like in the subspace topology? So we already have a topology on X. So on E, it will be equal to some E intersection G, where G is open in X. Now we are talking about the subspace topology on E. And we know that E is open. This G is also open. So this B is open in X. Now since this B is open and suppose it is non-empty, then this B intersect with A1. So there existed, so this is a non-empty open set in E. So this B intersection A1 is non-empty, which implies there exists a little a1 which belongs to B, which belongs to B and a1. That means this element belongs to E intersection G. So this a1 will be belongs to E. And a1 belongs to a1 also. So whatever neighborhood we are starting with, whatever open set we are starting in E, say B, we are getting an element from E intersection A1. So this E intersection A1 closure equal to E. The only thing is you have to make use of this alternative definition for this closure, A closure equal to X. Okay. So then we will move to the next question. Let A be a subset of R satisfying A equal to intersection N greater than or equal to 1, Vn, where for each N greater than or equal to 1, Vn is a open dense subset of R. Then which of the following are correct? So here someone earlier said some similar kind of While we were discussing something else, someone used some theorem.
Bayes category.
Bayes theorem. From Bayes theorem, which all options we can conclude?
First and fourth.
First and fourth option we can conclude. Now, what about option 2 and option 3? Will A be, can A be count? So Bayes theorem, whoever doesn't know, you can see from here. That is, let X be a metric space. Then the intersection of finite number of dense open subset of X is dense in X. And if X is complete, then the intersection of a countable number of dense open subset of X is dense in X. So here we have countable open dense subset. So that will be dense in R. So A is a non-empty set and A is dense in R. Now, can A be uncountable? So only thing is A is equal to intersection Vn. Can you produce some Vn's which are open and dense such that this A is uncountable?
Deleting
R minus Q is deleting
rationals.
Yeah, but yeah, correct,
enumerating
correct. We can delete singleton, say singleton n. Then A will be equal. Hello? Hello?
deleting rational set.
Whatever, deleting a countable set kind of thing. So I am deleting here, you can delete rationals one by one. Here I am deleting natural numbers one by one. So then what will be intersection of Vn?
R minus n actually.
R minus n. So will it be countable or uncountable?
Uncountable.
Uncountable. So this A can be uncountable. So we can eliminate this option 2. Now we have to check whether A is whether A is always uncountable. So can A be countable? Can A be written as intersection of Vn where Vn is dense open? Is it possible to write A? Is it possible to write a countable set in this fashion?
Take the set of rationals and V1 is equal to first rational subtract कर दें rationals के set से फिर. For example, if Q is a set which is R1, R2, R3 up to so on, then first V1 is Q except R1, V2 is Q except R2. Each one is dense, but their intersection is empty.
But will it be open? Q minus R1, will it be open in R?
No, ma'am. It will not be open.
So here we should have dense and open. So here, as you said, it is dense, but it is not open. So this example will not work. Or can you prove that A is always uncountable?
Miss, on the right side, countable intersection of open sets is A, and on the other side, countable union of closed sets.
Oh, okay, ma'am. X belongs to the intersection, so X belongs to each of the set which is open. So each open set must contain the interval, and the interval is uncountable.
But that interval need not contain, interval need not be contained in other Vn's. So that interval need not be there in A. We know that you are telling like this. If A belongs to A implies A belongs to Vn for all n. That means A is an so A is an interior point for all Vn. So there exists a neighborhood of A, say Un, such that this Un is contained in Vn. So, but this intersection of UNs need not be open.
Yes, ma'am.
So this argument will not work. Then what else we can think? What if A is countable? If A is countable, then we can give an enumeration for A, right? We have to prove that A is uncountable. So suppose if possible, we assume that A is countable. Then we can write A is equal to sum A1, A2, etc., A3, etc. Okay. Now, and also we know that A is equal to intersection of Vn, where n greater than or equal to 1. Now someone told us for, I don't know who said that, suppose Un equal to R minus A1, singleton A1, singleton An, then what will be intersection of Un? Suppose we are eliminating points from A one by one. What will be
R except A.
R except A. Now, is it an open set? Each UN, is it open?
Yes, ma'am.
Is it dense?
Yes, ma'am.
Yes. So this A complement, you are able to write it as the intersection of some dense open subset. Right.
Yes, ma'am.
So then this A intersection A complement, you can write it as intersection of n greater than or equal to 1 Vn, intersection with intersection Un. So all these Vn's are dense open set, all these Un's are dense open set. Altogether, it is an intersection of countable number of dense open subset. So this right hand side has to be dense by Bayer category theorem, Bayer's theorem. But what happens to the left hand side?
That is the empty set.
That is empty. So we are getting a contradiction here. So what is the reason for that contradiction? We assumed that this A is countable. So our assumption was wrong. So A will be always uncountable. Is it fine?
Yes, ma'am.
Okay. So now we are almost time. So we will skip some questions and we will move to the last part. So we can have some dessert and then wind it up. So for each alpha belongs to R, S alpha is equal to set of all x, y, z such that x square plus y square plus z square equal to alpha square. So they are the spheres. Let E is equal to union alpha belongs to R minus Q S alpha. Which of the following are true? The Lebesgue measure of E is infinite. E contains a non-empty open set. E is path connected. Every open set containing E complement has infinite Lebesgue measure. So now can you visualize this E? What is our S alpha? S alpha is equal to ordered pair x, y, z such that x square plus y square plus z square equal to alpha square. So this is the sphere with radius alpha. And E is equal to union R minus Q S alpha. So suppose this is our 0. So suppose this is our alpha. So this is our S alpha. Now we will take another irrational number. So here we are taking R minus Q. That is irrational radius. Now we will take another irrational number. We will draw another circle. Then likewise we will draw many circles. So this is our space E. So E will be circles with rational radius. Okay. Now, what will be the Lebesgue measure of E-com? We have to check what is the Lebesgue measure. Or okay. Now, what is the definition of Lebesgue measure? Lebesgue measure is the infimum of Lebesgue outer measure. You will be familiar with, like E is contained in. We will take an open, not open cover. We will take a cover E contained in union iron, and we will take the infimum of all those summation of length. So this is how we define the Lebesgue measure. So what is for what you can say immediately? Will it be connected? This E, will it be connected? Or can you produce a disconnection for E?
Yes, by taking alpha belongs to Q.
Yeah, if we take alpha belongs to Q, suppose this is an alpha belongs to Q, we will be able to produce a disconnection for E. By taking a circle like this and take the interior part intersection with E and its complement like this, we can produce a disconnection. So this is not connected. If E is not connected, obviously it will not be path connected. So we can avoid option 3. Now what about option 2? Will it contain a non-empty open set?
I think
This
Lebesgue
E-
measure using option A, we can avoid option B also. Lebesgue measure. If it is greater than 0, it contains an open set, but I think in this case it will be 0 actually. So it won't contain an open set.
What will be the Lebesgue measure of E?
I think it will be 0 in this case.
Why it is 0?
Because it just contains the boundary. We are considering in the case R2, right, ma'am?
Yes, we are considering only in R2.
Lebesgue measure, actually, that should be Lebesgue measure of.
What is the Lebesgue measure of R? Or what is the Lebesgue measure of Q complement in R? What is the Lebesgue measure of Q in R?
0.
0 Q complement infinite Lebesgue measure.
What is the measure of Q complement? It will be infinity, right? So, likewise, what will be the measure of E complement here? E complement is union of alpha belongs to Q S alpha, which is equal to summation measure of S alpha, where alpha belongs to Q. And each S alpha measure is 0. So the whole sum will be 0. So the measure of E complement will be equal to 0. Then what will be the measure of E here?
Infinite.
Yeah. So measure of E complement E will be infinite here. Oh. 1 minute. Yeah. So measure of E will be equal to infinite here. So Lebesgue measure of E is infinite. Lebesgue measure of E complement is 0. So the Lebesgue measure, so this option A is true actually. The Lebesgue measure of E is infinite. This is true. Now what about E contains a non-empty set, non-empty open set? Will it be true? If it contains a non-empty open set, it should contain a ball at least. So is it possible for E to contain a ball?
No.
No. Why?
If it contains a ball, then there will always some members of X alpha.
Yeah, if there will be some points with radius with rational radius. So a ball cannot be completely contained in this E. So we can eliminate that option also. Now what about option D? Every open set containing E complement has infinite Lebesgue measure. So what is E complement? E complement is union alpha belongs to Q such that S alpha. So the option is every open set containing E complement has infinite Lebesgue measure. Is it true? So here E complement is we will pick up alpha radius where alpha is rationals. And we will draw circles like this. Rational radius circles. So the option is every open set containing E complement has infinite Lebesgue measure. Is it true?
Only open set containing full E complement will
E complement is
full space.
Is it? Is it the only open set? Or else you come down to R and Q. Does there exist an open set containing Q having finite measure? So that we can replicate the same idea to this higher dimension as well. So does there exist an open set containing Q having finite measure? Q has an no.
Open set containing Q is R.
Yeah, R is one open set which containing Q, which contains Q. Is there any open sets which contain Q other than R?
Yes, R minus some element of Q complement.
That is also true, but it has infinite measure. So is it possible to find an open set containing Q which has finite measure?
No.
So this Q we will have an enumeration Q1, Q2, Q3, etc. Now consider B1 equal to ball centered at Q1 with radius say 1 in R. So we have real line. B2, consider the open ball centered at Q2 with radius half. B3, consider the ball centered at Q3 with radius 1/4. Sorry, B4 equal to ball centered at Q4 with radius 1/8. Go on like that. So if I consider union of Bn, will Q be contained in union Bn?
Yes.
This is contained in union Bn. Then this measure of Q will be less than or equal to measure of union Bn, which will be less than or equal to summation measure of Bn. Because we don't know whether these Bn's are disjoint or not, so that I don't know. But anyway, we can write less than or equal to by the countable additive property. We know that if A is A union B, measure of A union B will be less than or equal to measure of A plus measure of B. If it is disjoint, we can write measure of A union B equal to measure of A plus measure of B. But if it is not disjoint, we can say measure of A union B is less than or equal to measure of A plus measure of B. So likewise, we can say this is less than or equal to summation measure of Bn. Now, what is the measure of B1? What is the measure of B1?
Pi.
What? Okay, you are considering in R2. I'm asking in R only. R, we are taking a 1 radius ball. So the measure will be 2.
2.
In B2, the measure will be 1. Here the measure will be 1 by 2. Here the measure will be 1 by 4. So this will be less than or equal to 2 plus 1 plus 1 by 2 plus 1 by 4 plus 1 by 8 plus etc. What is the sum? 4, right? And this union BNs are open. Arbitrary union of open sets is open. So here you are getting an open set containing, so whole union BN, I am calling it as A. So I am getting an open set containing Q, which is of finite measure. Is it okay? Hello?
Yes, ma'am.
Okay. So there can be open sets containing Q with finite measure. It need not be infinite always. Okay. So now you can use the same idea for our problem. So here, instead of taking open intervals, there we can take spheres kind of things. So there can be open set containing E complement with finite Lebesgue measure. Like in here we have started with open intervals. So we were taking open intervals kind of thing corresponding to each rational number. So when it comes here, it will become, suppose we have a rational radius ball. We can take a annular region kind of thing, like fixing some volume like 1 by 2 power n. Likewise, we can make it smaller as much as we needed, thinner and thinner, make it thinner and thinner, so that this volume will be in this geometric series kind of thing, so that we can produce an open set which contains E complement but with finite Lebesgue measure. Okay, so I already exceeded my time, so we can do one. Is it okay? This question, is it okay for you now? This, especially this last option, is it fine? At least, do you got this idea to create an open set containing Q with finite measure?
Yes, ma'am.
Okay, so now we will skip this question. Actually, that was a very interesting question, but we don't have time. I will move to the last question and we will wind up here. This is a very easy question. Which of the following open covers of the open interval 0, 1 admit a finite subcover? First option is 0 to 1 by 2 minus 1 by n plus 1 union 1 by n with 1. Second option is 1 by n to 1 minus 1 by n plus 1. Third option is sine square n pi by 100, cos square n pi by 100. And fourth option is like that. So when you see such question, try to figure it. So how this open sets will look like? What happens if n equal to 0? If n equal to 0, what will be this open set? N equal to 1. This will be empty. This will also be empty. So we will get an empty set. Now what happens if n equal to 2? What will be the open set? 0, 1 by 2 minus 1 by 3 union 1 by 2 to 1. So this is 0 to 1 by 6 union 1 by 2 to 1. So our open set is 1 by 2 to 1 together with 0 with 1 by 6. Now what will be the open set when n equal to 3? For n equal to 3, it is 1 by 2 minus 1 by 4. So it will be 0 to 1 by 4 union 1 by 3 to 1. So how it will look like? This is 1 by 2. So 1 by 3 will be coming somewhere here. So 1 by 3 to 1 will be coming like this. And this is 1 by 6 actually. So 1 by 4 is lying somewhere here. So it is coming like this. Okay. So this side it is going on increasing. This side also it is going on increasing and increasing. So this sequence is monotonically increasing. Now if you find n equal to 4, what happens? If n equal to 4, it is 0, 1 by 2 minus 1 by 5, which is equal to 5 minus 2, 3 by 10. Union with 1 by 5 to 1. So 1 by 5 is coming somewhere here. So from here to here, we have 1 by 5. And from here to here, it is 0 to 0.333 kind of thing. So that will be coming like somewhat like this. So with this one interval itself, with this one element itself, we are able to cover the whole 0, 1. So 1 by 1 by 4. Hello.
One by 4. 1 by 5
I'm not. Okay. Sorry. Here. Where is my cursor? Oh. Yeah, 1 by 4 to 1. Anyway, that is also fine. That is, you are telling it is 4 here. So then our open interval will be coming from 1 by 4 to, instead of this. Still, we will cross this side. Because here it is 0 to 3 by 10. That is 0 to 0.333. Here it is 0.25 to 1. So anyway, that will intersect. So anyway, we will get open interval 0, 1. So this will produce a finite subcover. Now what about this option? This is 1 by n, n plus 1 minus 1 divided by n. So 1 by n, n divided by n plus 1. So how it will look like? Here we have 0, here we have 1. So when n equal to 1, 1 to 1 by 2. So it will not produce anything. For n equal to 2, 1 by 2 to 2 by 3. So 1 by 2 is coming somewhere like here and 2 by 3 is coming here. Now what about n equal to 3? N equal to 3, 1 by 3 to 3 by 4. That is, it is coming like, this is 1 by 2, this is 2 by 3. Now I want 1 by 3. This is 1 by 3 and this is 3 by 4. So next open set is coming like this. Now what will be the next one? N equal to 4, it will be 1 by 4 to 4 by 5. So it will be coming like 1 by 4 will be coming here. 4 by 5 will be coming here. So it is going on increasing, which is monotonically increasing. So will it produce a finite subcover?
No.
It will not produce a finite subcover. Now what about this option? Sine square n pi by 100, cos square n pi by 100. Can you put some random values?
Yes, n equal to 100.
Yeah, if you put n equal to 100, it is sine square pi and this is cos square pi. So from that element itself, we will be able to produce entire 0, 1. So this will have a finite subcover. Now this option you can check yourself. Like this is also, this as n increases, e power minus n decreases. As n increases, n plus 1 whole square increases, 1 by n plus 1 whole square decreases, 1 minus 1 by n plus 1 whole square increases. So as n increases, this left hand side is decreasing. So these intervals are coming like this, like this. Right hand sides are moving, increasing. So it is coming like this, like this. So this will also be able to produce a finite subcover. It is monotonically increasing. So if it has a finite subcover, we will take the large n. So whatever be the large n, this 0 will not be there in that set. So we will not be able to produce a finite subcover. So I will wind up here. So these are the references I used for topology part. I referred K.D. Joshi Introduction to General Topology. For that question related to holomorphic functions, open mapping theorem, I referred Kunnuswamy. And questions from functional analysis, I referred Limaye. So with this, I will wind up here. So,
hello, I am Alita Joseph from Changanasheri Assumption College. Thank you, ma'am. Today's session was really nice and helpful, even though we are graduate student. As already mentioned, I am a graduate student who just completed the second year. So the topics regarding the concept of topology was much unfamiliar to me. But from this class, I was throughout the class I was paying my attention fully because the way you discussed was really interesting. And this made up my mind to learn more about the concept regarding the topology. Thank you, ma'am. And thank you, sir, for organizing this.
Hello, miss. My name is Aksana. I have completed my MSc from NSS College at Palam and preparing for NET exam. And today's class was very useful. And topology is our favorite subject. And thank you for discussing problem from that section. Thank you.
Thank you, Arsana.
Hello, ma'am.
Hello,
Morning.
Yeah, 1 minute. Nanda Kumar is Nanda Kumar.
Hello, ma'am. Good morning, ma'am. Sorry,
Yeah.
good afternoon, ma'am. I'm from Tamil Nadu, Tiruchirappalli district, ma'am. I'm completed my master postgraduate. Today's session was very nice, ma'am. Thank you so much for this elaborate about the topology and functional analysis, ma'am. Ma'am, I have one question in our presentation, ma'am. That is q square from q square to 0, 0 to 1, 1. Ma'am, can we have a function like this as an example of x comma x from x comma y to 0, 0 if x is even, x comma y to 1, 1 if x is odd. Can we have a function like this, ma'am?
What about other function values for other points? Q is rational, so there can be points which do not belong to Z. So points like 3/2, what value you are giving?
Oh, okay, ma'am. I understand, ma'am. Okay, ma'am. We cannot say about 3/2 is whether even or odd. Yes. Okay, ma'am. Okay. Thank you so much, ma'am. Thank you so much, sir, for your work and for all this, sir. Thank you so much, sir.
Thank you, Nanda Kumar. Yes, Garima Kitawat. Yes.
Hello, ma'am. My name is Garima Kitawat. I am a first year student at IIT Madras. The questions discussed were really nice, and I like the way you draw the pictures for every questions, which made it easy for us to understand the problems. So everything was so good. So thank you, ma'am, and thank you, sir, for taking the initiative for this. Thank you so much.
For topology, if you draw pictures, you will get the answers quickly.
Yeah, thank you, Garima. Yes, others.
Hello, ma'am.
Yes.
Good afternoon,
ma'am.
Yeah, 1 minute. Sign up with this. Yes.
Hello, I'm Zainab Riza. I am from Sir Syed College, Talpramba from Kerala. Ma'am, the session was really helpful for understanding this new topic, even though I'm a BSc student. Thank you very much, ma'am. Thank you, sir.
Sign up with sir. Yes, Dharmendra, you can speak.
Good afternoon, sir. Good afternoon, ma'am. The session was very nice and interactive also. It is a little bit tough for me also. Can you share, ma'am, your PhD experience and what is your node area and topic?
Currently, I am doing PhD at IIT Madras in the area of partial differential equations. I am trying with eigenvalue problems in partial differential equations, but moreover, we are using the analysis tools, functional analysis. So mostly the equation will be from PDE, of course, but we are solving it using all the techniques that we learned in functional analysis, like this separable Hilbert space and all such properties we will be using to get a Rees representation theorem to get the existence of solution. So whatever you learn in functional analysis and topology, all these things we have to apply here. Like that, it is, my topic is like that. And now I am in the third year, so I was trying some problems. So I didn't solve a problem yet. I have to do it. Right now I am reading papers and then trying different problems, different approaches we have to try. Campus is really good. We have a very good environment, very good social circle also. Research is also going nicely.
Okay, thank you, Dharmendra. Others?
Hello, ma'am. I am Fatima Muhammad Ali. I am from 𝐂𝐸𝐲𝐻 College, Kerala. So I've already met you from the Meet the Scholars program. I am just a third year student also because I'm just practicing for the JAM exam. But I've just enrolled to this class and the class is very interesting. This is a real new topic for me, but still, I loved how you handled the session very, very much, ma'am. Thank you.
Okay. Maybe you will not understand many of the things because you are just third year. You didn't even might have real analysis will be new to you.
Yes,
that
ma'am.
will be just so obviously topology will be a little bit more than that. So you will not be able to understand it completely, but you can just see and then
Yeah, it is a new topic.
there is one topic, topology, that you will learn in your MSc, so that you can, when you study topology, you can just go through these questions again.
Okay, ma'am. Thank you.
Even if you understand nothing, any of the question, it is fine only for BSc final year students, because without knowing the very first definition of topological space, it will be difficult. But you just see and you can try. When you learn these topics, you can just try to solve these questions once again. At that time, you can watch it in YouTube.
Okay, ma'am. Thank you, ma'am.
Thank you,
Okay,
Fatima. Others?
Hi, sir. I'm Narumesa from TMG College, Kerala. And your class is very nice, really helpful. And thank you, sir, for the section. Thank you.
Thank you, Sarah. Okay, others, feel free to share your comments, share your feedbacks. Pooja, are you there?
Hello, sir.
Yes.
Hi, ma'am. Thank you so much for the section. I'm a final year BSc student. Even though I'm final year, I didn't understand anything, but yet it's interesting. I love the way you.
Yeah, it's normal only. Final year students, I can't expect that you should follow. It is completely new topic for you.
Yes, completely new topic. And thank you, sir, for this opportunity. Thank you.
Thank you, Pooja. Yeah, it's sometimes, final year students may not be able to follow, but it will be good to see there are some things beyond your topics in maths that will be really helpful, and so some kind of mathematical maturity you will acquire. Okay, any others?
Yeah, after learning real analysis, you can move to topological space.
In their system itself, there is some sort of topology is coming regarding the real line. So in that Bartle itself, there is a chapter, topology of R.
Oh, okay.
Even though they are not studying exactly the same definition in there, but it is there.
Yeah, in metric space, we actually in topological space, we are adopting all the nice behavior of this metric space, but without using the notion of metric.
Yeah.
So all this empty set is an open set, X is an whole set, R is an open set, or finite intersection of open set is open, arbitrary union of open set is open. All these things you are learning from real analysis. So that we are extending all such good properties. We are moving to some other space which have all such good behavior so that it will be easy to handle. And it will be a generalized version without using the notion of distance. So that is why we are introducing this topological space. Sometimes this distance cannot help us. Like even if we suppose we are solving a 3x3 Rubik's cube or something like that, whatever be its size doesn't matter. The technique is something different. Or there are problems like this Kannur bridge problem, in which it's about 7 bridges. So it's the problem is regarding the structure, how it is arranged. For all such problems, this distance doesn't play a role. But we need some nice properties of this metric space so that we will be able to solve such problems. So we will so that's why this topological space came into picture, and then more studies came in that area. After learning your metric space, then you will be able to come back to this topological space. It's a very interesting topic. The only thing is, sometimes we will be reluctant to draw pictures in topology. Even if I referred from 𝐂𝐬𝐩𝐽, but I didn't saw any single drawing in that book regarding the definition. Few pictures like topology, sine curve, Broom space, Combe space will be there. Other than that, all the theorems, it will be written like theoretically. So the only thing is we have to draw pictures correspondingly so that we will get the idea what to prove. If simply the statement start from let X be a topological space, just randomly draw a space X. And if there is X is an interior point, you just draw a point X, you just draw a circle or sphere containing that X just to get an idea. So likewise, when you learn topology, you draw pictures for each and every theorem that you are going to study. So then it will be easy to pick up the concept, as well as you will be able to solve these problems in competitive exams. The only thing is we have to draw pictures for topology. So you can save time and you will get what I noticed is in topology, syllabus is very less for in net exam. There is no advanced topics like quotient topology or algebraic topology, that's fundamental group, all such things are not there. It's just points in topology. So if you learn this basics, you will get 12 marks easily. Only 12, around 12 marks it will be asked per year. So it's such a very small topic, but if you study it thoroughly, you will be able to answer. In whatever way they construct the question, you will be able to answer. That's it.
Yeah, Jiya, you are muted, I think.
No.
Yeah, your voice is not coming. Yeah, it's okay now.
Okay, fine.
Yeah, by the way, let me point out that Mangas will be a good choice if you would like to see pictures in topology. James R. Mangas, a first course in topology. Topology, a first course. That will be a nice choice. Yeah, any others? Okay, I think. Yeah, Shri Dharal, yes.
Thank you so much, ma'am. It was a wonderful session, and for example, that question where you defined how we get finite, like from Q we can define a finite measure set. It was really interesting. Thank you so much, ma'am, and thank you, sir, for organizing the session.
Ruby, could you introduce yourself from your institute?
Sir, I'm Shriti Baral. I have completed my MSc from Delhi University
Okay.
in 2020.
Okay.
And I'm
Thank you.
preparing for NET.
Yeah, thank you, Shruti.
You can
Actually, I'm
refer
a
this
housewife,
topology.
so after I've already attempted twice the NET, but because I'm a housewife, so I don't get much time to prepare. So,
Okay.
thank you so much.
Okay, do a little bit hard work this time. Certainly, luck will be with you. All the very best for your NET examination.
You can refer Kumaration's book on topology of metric spaces. That is also a nice book, so that you will get an idea, clear idea.
Yeah. There is another one in Google. If you search, there is a book with namely Topology Without Tears. That book is also a very nice choice. Yeah, Lakshmi.
If you want to do some problems, you can read Simmons' book.
Yeah.
And Parthasarathhi's book is also very good. K. Parthasarathi.
Yes. Yes.
Hello, sir. I am Lakshmi. I am from TMG College, Tirur. Thank you, ma'am, for this class, wonderful class. It was so interesting and informative. And thank you, sir, for conducting this class. Thank you.
Thank you, Lakshmi. Hey, is there anyone else who would like to make any comments? Otherwise, we will wind up the session here. So thank you everyone for the patient listening, and hope that today's session you have really benefited out of this, will be useful for your exam. Once again, I would like to thank Jiya for being with us throughout the journey of Math Aspirants, and wish you all success in your future academic career. Thank you.
Thank you so much.